Alright, so let's have a look at ionic equations. Now, an ionic equation is a really useful way of showing what's happening in an ionic reaction. Alright, so let's have a look at ionic equations. Ionic equations are really useful ways of showing what's happening in a solution, particularly in instances like batteries, etc. Like, they're really, really useful. They cut out a lot of the nonsense. So I'm going to cut out the nonsense and we'll move on. So the first thing we're going to look at is we're going to look at a total ionic equation. Now, in a total ionic equation, now what you're used to seeing is something called a molecular equation. We'll see that in a second. But in a total ionic equation, all your dissociated species, so these are your ions which are dissolved in solution, are written as ions, and all species are included. That's why it's called total. So dissociated species, by the way, just as a reminder, is something which is dissolved in solution. So here we have our molecular equation. We have silver nitrate, sodium chloride, so aqueous, aqueous. All right, that goes to, that arrow means goes to, not equals, silver chloride as a solid. Remember, silver chloride is a precipitate, and sodium nitrate as a solution, or aqueous. We show all of our aqueous, so all of our dissociated ions, in an ionic state. That means it looks like this. So we have silver plus AQ. Now it's balanced. There was no balancing needed for this equation, but it is balanced. It needs to be balanced, I mean. Nitrate with a minus. Okay, so nitrate has a valency of -1. Sodium has a valency of plus, or sorry, 1. Chlorine has a valency of -1. And you see how they're all written out. Everything's there. Silver chloride is a solid, so it's not dissociated, so it gets written in its molecular form. Okay. However, the sodium is still dissociated, so it's written like this, and the nitrate is still dissociated, so it's written like this. Now, what you'll notice is we've got some spectator ions. A spectator ion is an ion that remains unchanged in solution. Okay, so it's pretty much the same on this side as it is on that side. It's called a spectator ion because it's not doing anything. It's not changing at all. It's just sitting there as it was before. So nitrate as aqueous, nitrate aqueous. Cool. Sodium aqueous, sodium aqueous. They did not change. They are spectator ions. Now, if we're going to draw a net ionic equation, basically we only draw the species that change in some way. Okay? Unchanged ions, or our spectator ions, don't get a look in. That we cancel them out, and because they're the same as both sides, so they're not having an effect. So here's our total ionic equation. It's the same one. So the first thing you want to do is you want to cancel out your spectator ions. Done. This now actually leaves a much, much simpler net ionic equation. And this is really important, by the way. In industry, if this is what you're worried about, these spectator ions, as long as they don't cause another precipitate to form or something like that, they're not that important. So you might be able to use other sources of silver, other sources of chloride to make your silver chloride. That's not the important part. The important part is this, because no actual reaction is happening with these guys. They're just staying in solution, bouncing around the place. So let's have a look at a more complex example. So here's our molecular equation. We've got 3 calcium nitrates in aqueous, 2 hydrogen phosphates gives us calcium phosphate. And you can see that the reason it's more complex is we've got more subscripts and more coefficients out the front. And then we've got hydrogen nitrate, or nitric acid. So our total ionic equation looks like this. All right, so we go calcium, blah, blah, blah. And we can see, this is what makes it more complex. We have 6 nitrates, because here we have nitrate times 2 times 3. So 3 times 2 gives you 6. 2 times 3, so 2 there, times 3 gives you 6 hydrogen ions. And you can see how that's all shaking out. 2 times phosphates, there. Now here we have our calcium phosphate as a solid, our 6 hydrogen ions, our 6 nitrate ions. I want you to pause the video and see if you can have a guess or have a go at working out the net ionic equation first. Go now. Alright, so let's see what you got. We cancel out the nitrate. Okay, nitrates are gone. Then we cancel out the hydrogens. Hydrogens are gone. And we get a much simpler net ionic equation. 3 calcium 2 plus 2 phosphate 3 minus goes to calcium phosphate. I hope that made sense. If you have any questions, feel free to ask them in the comments below. We'll get back to you as soon as we can. And thanks for watching.